Level 0. A slow black mass is crossing the road. It has been moving since last Tuesday. It doesn't make a sound. There is no warning siren for this. No evacuation order yet because technically, the lava is still 2 streets over. Then it isn't. That is Pahoehoe. Say it Pahoehoe, the gentlest version of something that can erase a neighborhood. Built most of the big island of Hawaii by doing exactly that, slowly over millions of years, one thin sheet at a time. Pahoehoe erupts at around 2,100 degrees Fahrenheit, 1,150 degrees Celsius, but flows with viscosity low enough to spread across the ground in continuous sheets, cooling on the outside while staying molten underneath. The surface wrinkles back on itself as it moves. The texture it leaves behind looks like coiled rope, braided leather, the skin of something large that stopped breathing mid-exhale and froze. Geologists call it ropey lava, the actual technical term. It earned it. While the surface cools, lava keeps moving through the interior in lava tubes, insulated tunnels that preserve heat across many miles of travel. When the eruption ends and the lava drains, the tubes hollow out. The Kazumura Cave formed this way: 40 miles, 64 kilometers long, one flow, one eruption. In 2018, Pahoehoe flows from Kilauea's Lower East Rift Zone spent weeks crossing residential streets in Leilani estates. Not racing, not surging, creeping steadily through subdivisions people had lived in for 30 years. By the time some homeowners grasped that the lava had no intention of stopping, the road out was already gone. Pahoehoe is the version of this story where you have time to think. The next type removes that option. Level 1. Some Hawaiian linguists suggest ʻAʻā got its name from the noise people made stepping on it barefoot. That probably isn't the official etymology. Nobody seems in a hurry to correct it, because it sounds exactly right. ʻAʻā lava starts from the same basaltic magma as Pahoehoe. The difference is what happens during travel. Move faster, lose dissolved gases more quickly, and viscosity climbs. The smooth surface fractures. What was once continuous and ropey tears apart into a churning mass of jagged, angular clinker that looks like someone detonated a gravel quarry and left the debris smoldering. The interior stays liquid the whole time, so the flow advances as a grinding wall of broken rock pushed from behind by a molten core, sometimes 10 feet, 3 meter tall at the front, constantly collapsing forward as fresh lava shoves through the base. Researchers who have stood near active ʻAʻā flows describe the sound as the most unsettling part. Deep, relentless grinding and clicking, low frequency like the earth processing something very large between its teeth. On flat ground, walking pace is enough to stay ahead of it. On steep terrain, flows have clocked over 1 mile per hour, 1.6 kilometer per hour. The problem is what running from ʻAʻā actually requires: sprinting across the razor-edged rubble field it just deposited in volcanic heat, with no flat surface to plant a foot. In 1950, a Mauna Loa ʻAʻā flow covered 15 miles, 24 kilometers, in under 3 hours. Pahoehoe turns into a ʻAʻā mid-flow with no warning. The same eruption, the same magma, converting partway down the slope as speed and gas content shift. You cannot predict which you will get. Both types share one thing: people have been watching them, photographing them, and occasionally dying near them for centuries. And yet 75% of all lava on Earth erupts where no human will ever see it. In a place volcanically active since before animals existed. Level 2. The ocean floor is not a flat, featureless plain. Running through it for 40,000 miles, 64,000 kilometers, longer than any mountain range on land, is a continuous volcanic ridge system where tectonic plates pull apart and magma fills the gap. It is erupting right now, constantly, in every ocean basin simultaneously, building new seafloor in total darkness at a depth of roughly 2 miles, 3.2 kilometers. When magma pushes into seawater, the outer surface flash cools in milliseconds. A glassy skin locks around the molten rock almost instantly, but the interior is still pressurized, still pushing outward. The skin stretches, bulges, ruptures at the weakest point, and a new lobe squeezes through before that one seals. Repeat this across an entire ocean ridge and you get pillow lava, rounded, blobby stacks covering the seafloor in piles that look absurdly like cushions. Deep-sea submersible footage of active pillow formation is one of the stranger things geology has produced. Orange lava meeting black water, the surface crystallizing to glass mid-push, new pillows forming in silence 2 miles, 3.2 kilometers, below any daylight. No eruption column, no sound, just construction at the bottom of the world at roughly the pace your fingernails grow. The Atlantic Ocean floor is entirely this material. Every square kilometer from the mid-Atlantic ridge outward was once basaltic magma erupting at that ridge, cooling to pillows, spreading outward over 180 million years. The seafloor is not ancient and static. It is geologically young and still being made. When geologists find pillow lava preserved in mountain ranges, they stop and look. It means oceanic crust shoved onto a continent through a tectonic collision millions of years ago. The pillows are proof of a vanished sea sitting in a mountain that didn't exist yet when the lava formed. Pillow lava is quiet, pressurized, patient. Bring a submarine volcano within 650 feet, 200 meters of the surface though, and patience becomes the wrong word for what happens next. Level 3. Shallower water means lower pressure, which means the water boils the instant it contacts erupting magma. That boiling is not gentle. It is violent, instantaneous fragmentation, lava shattering into thousands of glassy shards in a fraction of a second. The material produced is called hyaloclastite, volcanic glass rubble, and it piles around shallow submarine vents in mounds that grow upward until, eventually, one of them breaks through. November 1963. Fishermen south of Iceland see the ocean boiling, steam columns rising from open water. An eruption had started on the sea floor and was climbing toward them. Within days it breached. Within weeks a new island existed. They named it Surtsey, and it grew to 560 feet, 170 meters, tall in months. The early phase was chaos. Every time seawater flooded the vent, steam explosions shredded the eruption column, throwing lava fragments and ash into dark cauliflower-shaped plumes that crackled with continuous lightning visible from the Icelandic mainland. The island was constructing and destroying itself simultaneously, blowing its own material into the air and welding it back together on the way down. Once the vent rose above sea level, water access ended and the explosions stopped. Lava flowed normally, the island stabilized, and scientists have been watching it since, tracking the arrival of life on bare volcanic rock. Bacteria first, then mosses, then nesting seabirds, then soil. Surtsey is the most complete documentation of ecological colonization, nothing that science has. Right now, seamounts are doing this beneath every ocean, building upward, getting close. Some will breach within thousands of years, most will erode before they get there, and a few will become islands. The seafloor is always attempting to surface, but all of this, everything so far, flows outward and dissipates. What silica does to magma is the opposite of that. It traps everything inside, and eventually something has to give. Level 4. The variable that changes everything is silica. Low silica content makes magma fluid, runny, willing to travel. Raise it enough and the magma becomes thick, sticky, reluctant. High silica magmas don't pour out of a volcano. They squeeze out under enormous pressure and pile directly on top of themselves at the vent, building thick, stubby structures called lava domes. Domes grow slowly, weeks, months, sometimes years. Fresh magma pushes up from below, inflating the dome from inside while the outer surface cools into a brittle, fractured crust that creaks, steams, and occasionally drops hot rock down the flanks. From a distance, a growing dome barely looks like it's moving. That is the problem. The entire dome is under internal pressure. One surge of fresh magma, one structural weakness, and the dome collapses. The pressurized interior releases at once, and a pyroclastic density current accelerates down the flank. Superheated gas, ash, and volcanic fragments at hundreds of miles per hour. Internal temperatures exceeding 1,300 degrees Fahrenheit, 700 degrees Celsius. There is no running from it once it starts. Pyroclastic currents have killed more people than lava flows across all of recorded volcanic history. They killed Pompeii in 79 AD. In 1991, 43 observers and volcanologists died on Unzen volcano in Japan when a dome collapse sent a current down a flank assessed as safe. At Soufriere Hills on Montserrat, collapses have been recurring since 1995, and the southern half of the island is still a permanent exclusion zone. High silica lava doesn't behave. It accumulates pressure until a release becomes inevitable, and when it goes, it takes the surrounding landscape with it. There is a volcano in Tanzania that has been doing the opposite of all of this for longer than any record exists, erupting a lava so cold and so strange that the scientific community spent years arguing over whether it qualified as lava at all. Level 5. The lava coming out of Oldonyo Lengai in Tanzania is approximately 930 degrees Fahrenheit, 500 degrees Celsius. Normal basaltic lava erupts at over 2,000 degrees Fahrenheit, 1,093 degrees Celsius. Oldonyo Lengai is producing the coldest lava on Earth, and it is so far outside the normal parameters of volcanism that when Western geologists first analyzed samples in the mid-20th century, there was a genuine scientific argument about whether the material was even volcanic in origin. It is, just barely by conventional definition. Carbonatite lava is dominated by carbonate minerals instead of silicates, sourced from a part of the mantle that produces almost nothing else on the planet today. ʻAʻā is the only active carbonatite volcano on Earth. At an eruption, carbonatite is thinner than water. It spreads in fast, shallow sheets that look wrong at a glance, too dark, too fluid, moving too quickly for something coming out of the ground. Daylight robs it of any orange glow. Fresh flows look like engine oil across pavement. At this temperature, researchers have stood at the crater rim, watching active flows below them. No other active lava allows that. Then the atmosphere gets involved. Within hours of erupting, carbonatite reacts with moisture and begins crystallizing, lightening from black to gray over days, then to near white within weeks. The flanks of ʻAʻā look from a distance like old, compacted snow. When rain hits, the deposits dissolve. The mountain continuously prints and erases its own surface. Ancient carbonatite deposits survive on multiple continents, evidence that this style of volcanism was once far more widespread. At some point, Earth nearly stopped producing it. The reason is still debated, which means something about this planet changed in a way science hasn't fully explained yet, and there is no guarantee it won't change back. Level 6. The Archean Eon ended roughly 2.5 billion years ago. Before that, Earth's mantle ran hotter. The crust was thinner, more permeable. Magma broke through more often, at temperatures with no modern equivalent. What erupted was called Komatiite, and nothing volcanology has documented since comes close. Estimated eruption temperatures: 2,900 to 3,400 degrees Fahrenheit, 1,600 to 1,870 degrees Celsius, nearly double the hottest basaltic lava active today. At those temperatures, viscosity dropped to near water levels. Komatiite didn't build flows. It surged across the ancient landscape in thin, scalding sheets, covering enormous areas before the surface had time to cool, at speeds no modern volcanic flow approaches. It survives in the geological record as a spinifex texture, long, blade-shaped olivine crystals oriented in radiating patterns through the rock. Sliced and polished, Komatiite looks almost deliberately designed. The crystal blades exist in the Pilbara Craton of Australia, the Kapval Craton of South Africa, the Superior Province of Canada, some of the oldest exposed rock on the planet. Modeling what a komatite eruption looked like produces numbers that sit uncomfortably. Thermal radiation from an active flow would have been lethal at distances modern volcanologists consider routine. Contact with water bodies likely triggered explosive steam events across the leading edge. Some researchers propose that the largest komatite episodes contributed to extinctions of Archean microbial communities that had persisted for hundreds of millions of years before the flows arrived. The last confirmed komatite eruptions occurred around 90 million years ago on what is now Gorgona Island off Colombia. A final echo before the temperatures required simply became unavailable. The planet that produced it is inaccessible now, locked inside geological time, its lava surviving only in crystals that record a heat nothing alive has ever been near. But Komatiite was a localized event compared to what the mantle is capable of when it really decides to remodel the surface. Level 7. A flood basalt eruption doesn't come from a single volcano, it comes from a region. Thousands of fissures splitting open across hundreds of thousands of square kilometers, stacking lava until the land underneath is simply gone, buried under rock sometimes 1.2 miles, 2 kilometers thick. The Siberian traps erupted around 252 million years ago. Estimated lava volume between 1 and 4 million cubic kilometers over roughly a million years. Mount St. Helens in 1980 produced about 1 cubic kilometer of material. The Siberian traps matched that and kept going, millions of times over. What followed was the Permian-Triassic extinction, the worst biological catastrophe in Earth's history. Approximately 96% of all marine species were eliminated, around 70% of terrestrial vertebrates. Over tens of thousands of years, volcanic carbon dioxide and methane pushed global temperatures up, ocean chemistry degraded, seawater oxygen collapsed, and food chains across every ecosystem unraveled from the base. Recovery took tens of millions of years. Some ecological structures never returned. The Deccan traps erupted 66 million years ago alongside the end Cretaceous extinction. The asteroid Chicxulub is the accepted primary driver, but the Deccan eruptions were destabilizing ecosystems before the impact and continued for hundreds of thousands of years after. Two catastrophes overlapping, each amplifying the damage the other caused alone. Flood basalt events appear in the geological record roughly every 100 million years. Mantle hotspots sit beneath Yellowstone and the Afar Triangle in East Africa today, with material closer to the surface than standard models predict. None are producing flood basalts. Not yet. The last one was the Columbia River basalts, roughly 16 million years ago. The hotspot that caused them is still active. The conditions that produced the Permian extinction are not an anomaly. They are a feature of how this planet behaves, and they will recur. The only question is, what will be here when they do? Level 8. The James Webb Space Telescope observed a planet called 55 Cancri E in 2024 and detected something striking. Its atmosphere changes irregularly, in patterns consistent with active volcanic outgassing at planetary scale. The leading explanation is that 55 Cancri E has no crust. Its entire surface is a global magma ocean, molten rock pole to pole, potentially thousands of kilometers deep. Earth had this once. 4.5 billion years ago, after the moon formed, a global magma ocean existed here for tens of millions of years before cooling into a solid crust. On a planet orbiting its star every 18 hours at surface temperatures around 3,100 degrees Fahrenheit, 1,700 degrees Celsius, that cooling never completes. The star keeps adding heat faster than the planet can shed it. On 55 Cancri E, the idea of a lava flow is meaningless. There is no ground to flow across. The surface is the magma. Convection cells circulate molten rock from depth to surface and back continuously. The permanent day side may be hot enough to vaporize silicate minerals into the atmosphere. The night side might allow brief crystallization before that material convects back and melts. The atmospheric data fits this model. The physics isn't speculative. A rocky planet too close to its star will not solidify. It will remain molten for as long as the star burns. But here is where it stops being a story about somewhere else. The magma ocean that covered early Earth didn't disappear. It went underground. The mantle beneath your feet is still largely molten. The crust averages about 25 miles, 40 kilometers, thick over continents, considerably less beneath the oceans. Below that, the same material that once covered the entire surface is still there. Still hot, still moving. Not as a relic, not as something cooling towards stillness. As an active system, under pressure, looking for exits. It finds them. Flood basalts happen when it punches through on a regional scale, stacking lava across hundreds of thousands of square kilometers. Komatiite happened when the mantle ran hotter and broke through more easily, surging across the ancient surface at temperatures nothing alive today has ever been near. Every eruption in the geological record, every lava type that exists, is an instance of the interior testing the surface and occasionally winning. The crust is not a sealed container, it is a temporary arrangement, thin in places, fractured along plate boundaries, perforated by hotspots. The mantle doesn't wait. It circulates on timescales measured in millions of years, and periodically, in ways the geological record documents clearly, it breaks through in catastrophic ways. 55 Cancri E is not an exotic outlier. It is a data point on a continuum that includes Earth. The difference between that planet and this one is a matter of orbital distance, a number small enough that the gap feels less like a safety margin and more like a close call that has been ongoing for 4.5 billion years.